Let's continue with our discussion on limit state method of design. This is the chapter 2 in our video lecture series on design of reinforced concrete structures. So in our previous lecture, we looked at these two topics. First, we looked at the safety and serviceability requirements and different limit states of structure. And then we discussed on the concept of design strength of materials and design loads. We will discuss these three remaining topics today here. Okay, first let's look at the idealized stress-strain diagram of concrete and steel. This idealized stress-strain diagram has been recommended by our code of practice, that is IS 456. Some idealizations have been made in relation to the or in comparison to the actual stress-strain diagram for concrete and steel, and thus we have derived the design curve that we will be using in our analysis and design of reinforced concrete structures. In this slide, if you look at the stress-strain diagram on the left hand side, we have the actual stress-strain diagram for concrete that we generally get from the laboratory test. You can see various diagrams here. For example, these curves which have been made with dashed lines, these are the stress controlled curves. You can see here the rate of change of stress with respect to time is constant for these curves, whereas for the curves made with this solid line, these are the strain controlled test that is performed on the concrete. And for this curve, the rate of change of strain with respect to time is constant. So these dashed lines and these solid lines represent the actual stress-strain curve of concrete that we get when we perform different tests on them. But instead of using this actual curve for our design, the stress-strain diagram for concrete has been idealized to the curve that is seen here on this right-hand side here. You can see here stress function is plotted on the y-axis and then strain on the left on the x-axis. And if you see here, these curves are parabolic in nature. You can see this three curves which are parabolic for up to a strain value of 0.002 here. So up to a strain value of 0.002, these curves are parabolic, while for the strain between 0.002 and 0.0035, the curve is considered a straight horizontal line here. This 0.0035 is the value of limiting strain, which we will discuss in our upcoming slides here when we discuss some assumptions for limit state of collapse or flexure. But just remember that instead of using these irregular curves on this left hand side, instead we have now used a combination of parabolic and horizontal curves here. So this first curve at the very top, this is the characteristic curve. This is the characteristic curve for concrete, and we will use this curve to derive the design curve, which is our curve at the very bottom here. This is our design curve, and we will use this design curve in the design of our reinforced concrete. So you can see here, if this curve at the very top represents the characteristic curve, then this characteristic curve represents the characteristic strength of our concrete, which is given as FCK. Now this characteristic strength FCK has been reduced by some amount. That means we have only used here 67% of characteristic strength and derived this second curve here. So why has this curve been reduced to this curve? There are primarily two reasons. So first reason is that whenever we want to test concrete in our lab test, when we want to perform lab test for our concrete, then generally what Indian codes prescribe is that we make a cube of size 150 mm over 150 mm over 150 mm, and we test the strength of this cube in our lab. Whereas if you compare this with British code or European codes, then those codes prescribe, or those codes say us that to perform the lab test of concrete, we have to construct a cylindrical shape or a cylindrical mound, which is generally 150 mm in diameter and 300 mm in height. So to account for the differences in strength that we get while performing lab test for this cube and for this cylinder sample, we generally reduce the value of characteristic strength that we get from this. For example, suppose that by performing for the same sample of concrete, if we perform cube test, then we get its characteristic strength as FCK, whereas if you use the same sample of concrete to perform this cylinder test, then we only get about 80% of this characteristic strength, that is about 0.80 FCK. So one reason to use the reduced value of the characteristic strength is this, the use of different kind of specimen to do the lab test. And second reason is that since we only use a cube to know its strength in lab, but in actual when we build our reinforced concrete structures, then they may not always be cube. They may be of different shapes. Our beam, column, slab may be of different shape, and also that the size of our structural elements in actual is very much large as compared to this small cube of 150 mm size. So what generally happens is that when we compare the strength of this cube to our actual structural elements, then the design value or the characteristic strength of those actual elements come out to be of a lesser magnitude as compared to this cube. For example, if this cube has the characteristic strength as FCK, then the strength of our actual structural elements may come out to a value of about 0.83 or 0.85 of FCK. So you can see that although the actual characteristic strength is FCK, these two factors may lead to a reduced value of FCK in our actual structure. So to account for these two factors, if you multiply this 0.80 by 0.85 here, then almost or near about we get the value to be 0.66 or 0.67, and we use this 0.67 value here to get the characteristic strength. And further, we know that the partial safety factor for concrete is given as gamma m, which is equal to 1.5. Now we have to divide this 0.67 FCK by the value of 1.5, so that this comes nearly equal to 0.45 FCK. Hence this curve, which represents 0.45 FCK, is our actual design curve now. So even in our idealized stress-strain diagram for concrete, we have to derive the value of this design curve from our characteristic curve, and then use that design curve in analysis and design of our reinforced concrete structures. So this is about the stress-strain diagram of concrete. Now if we look at the stress-strain diagram for steel, then we have to look at the diagram for mild steel, which is given on this left hand side, and another is for the cold worked bars, or you can say the high yield strength deformed bars, HYSD bars, on the right hand side. So in general or in actual, when you perform the lab test on your steel elements, then the general stress-strain diagram may come out to be like this. So this is just an example. The actual stress-strain diagram may differ. For example, up to this point A you may consider as proportional limit, point B you may consider as elastic limit, then you get the upper yield point, then you get this lower yield point, then you get this ultimate tensile strength point, and then you finally get the point of failure or breakage here. In this way, you may get this somewhat irregular kind of curve for your stress-strain diagram of steel when you perform actual lab test. However, in our design of RCC structures, now we will idealize this curve. In case of mild steel, we have a bilinear approximation here. Bilinear approximation. So bilinear approximation means now this whole curve has been idealized as two linear lines or two straight lines. One is this line and another is this line here. So generally what happens in mild steel is that the value of this Fy or the value of this yield stress is definite or fixed, you can say. So if Fy is the value of yield stress in our steel here, now what we will do is we will divide this yield stress by the partial safety factor for material of steel, which is given as equal to 1.15. So if you divide Fy by 1.15, you will get 0.87 Fy. Now this will be our design curve for mild steel. But if you look for the cold work bars or cold twisted bars in this right hand side, the value of Fy is generally not fixed, or if we say that our bar is Fe 415 grade or Fe 500 grade bars, then these letters 415 and 500 represent the value of yield stress. In case of mild steel, it is Fe 250 and 250 Newton per mm square is the value of our yield stress or Fy value. So this value of Fy may be fixed for mild steel bar, but the value of Fy for these cold twisted bars, they may vary a little. So what we do for these cold twisted bars is that we use this approximate design curve Fy over 1.15, which comes out again equal to with 0.87 Fy for a value of Fy between 0.80 Fy and the total Fy. So I repeat it again, for the value of this Fy or yield stress between 0.80 Fy and Fy, we use this approximate design curve, which is again given by dividing this Fy by the partial safety factor for steel, which is 1.15. Hence, the design stress comes out to be 0.87 Fy, which is the same as for this mild steel here. So this is about the stress strain diagram for steel. Now let's go to our assumptions for limit state of collapse in flexure. These assumptions are the very basis which governs our design for limit state in flexure here. So this is given in clause 38.1 of our IS code 456. Let us see what these assumptions are. For first, plane sections normal to the axis remain plane after bending. So what does this mean is that what this first clause tells us is that suppose we have a beam here and this beam is subjected to some value of uniformly distributed load in this way. Now the beam may bend in this way here, creating compression at these top fibers and then tension in these bottom fibers. And if you look at the cross section of this beam here, if we suppose that this is a rectangular beam, then this section of the beam, which is plane before bending, also remains plane after bending. So what does this imply? This implies that the strain across the depth of the section is varying linearly. For example, if you look at the diagram here, we have a rectangular section of width B and total depth D. Let us just ignore this reinforcement for now. We will deal with this later. Then you can see that the strain profile for this section is linear. This strain varies from some value at the bottom, which is in tension, as we saw from this diagram, and then the strain value is 0 at some point along this at the middle of this section, and finally again there is positive strain at the very top, which is a value of 0.0035. So you can see that the variation of strain is linear here. So why do we take the strain to be linearly varying? Because this has been verified by numerous tests on reinforced concrete beams. Hence we have this first assumption that plane section normal to the axis remain plane after bending. In number 2, the maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. We saw in our idealized stress-strain diagram of concrete also, you can see the maximum strain that we have taken here is 0.0035. So we assume that the maximum possible strain in concrete at the outermost compression fiber is taken as 0.0035 as shown in this diagram also. So this is the value of strain which our beam section or our reinforced concrete section assumes at the point of maximum moment. That means if we have the maximum moment capacity, the maximum moment carrying capacity of our reinforced concrete section is calculated, at that point of maximum capacity, the maximum strain at this compression fiber will be 0.0035. Remember that this value of 0.0035 may be subjected to large variation because of different factors such as rate of deformation, loading time, grade of concrete, shape of cross section. But our code gives us this value of 0.0035 because in most of the cases when using this value, very conservative results we get, and in case of pure bending, this value is also accepted. Third case, for design purposes, the compressive strength of concrete in the structure shall be assumed to be 0.67 times the characteristic strength. The partial safety factor 1.5 shall be applied in addition to this. We have already discussed about this in our idealized stress-strain diagram for concrete, how we got this 0.67 and how we get, after dividing 0.67 by 1.5, how we get 0.45 FCK. The tensile strength of the concrete is ignored. You may want to calculate the actual moment carrying capacity by considering also the tensile strength of concrete, but that sort of refinement or that level of analysis is not required. We can generally ignore the tensile strength of concrete. For design purposes, a partial safety factor of 1.15 is used for strength of steel. We have already discussed this also. And finally, the maximum strain in the tension reinforcement in the section at failure shall not be less than this value here, Fy over 1.15 ES plus 0.002. So why this value here? Let's see that. Why do we need a value of maximum strain in the tension reinforcement in the section at failure? See, we have two kinds of failure. One is the, you can say that, brittle failure. We will discuss more about this in our next chapter also, and another is ductile failure. So our concrete failure may be of two types, brittle failure and ductile failure. Brittle failure is the case when the concrete fails at first. That means concrete fails before the failure of our reinforcement bars or steel bars. And ductile failure means where our reinforcement steel bars fails and then only our concrete fails. So this brittle failure in which our concrete fails at first is sudden nature, and we generally try to ignore, or we generally try to ensure that such type of failure does not occur in our structure. Because these failures are sudden and our structure does not give us any type of warning for brittle failure, we generally try to ensure that such failure do not happen in our structure. We always try to ensure this ductile failure where our reinforcement bars or our steel bars yield at first and then only our failure of concrete occurs. So the general principle while designing the reinforced concrete structure is to ensure ductile failure, that is the tensile reinforcement. I have said tensile reinforcement. I am generally showing at the bottom of this diagram because we are just supposing that our beam, we have supposed a beam section here which is subjected to a loading like this, and it is bending in such a manner such that the tension zone lies at the bottom and the compression zone lies at the top. So we try to ensure that in this tension zone which lies at the bottom we have tension reinforcement, and that tension reinforcement yields first before the failure of our concrete structure. So our maximum strain in the tension reinforcement in the section at failure shall not be less than this value here. So first of all, let us look at this value here. Fy means the yield stress or yield strength of our steel, and Es is the value of the modulus of elasticity for steel. So in our code limit on this maximum strain, this first term corresponds to the strain at the yield stress. That means Fy for the case of mild steel and other types of steel bar which have a well-defined yield point. So for mild steel or any other type of steel which has a well-defined or fixed value of Fy, this is the value of limiting strain or the maximum strain. But for our high strength bars or for our cold twisted bars, we do not have a fixed value of Fy. So only ensuring that our section at failure reaches this strain value may not be sufficient. Hence, we take this conventional value of or additional value of 0.002 in addition to this Fy over 1.15 ES. So how does this value of 0.002 comes? Because what we generally take yield stress Fy, if we do not have a fixed value of Fy, then we generally take Fy as 0.2% proof stress. That means if we have this stress strain diagram curve, then this value, which is the value of 0.2% proof stress, is generally taken as the value of Fy. So 0.2% means 0.002, and this value is added to this value to know the value of maximum strain here. So these 6 are the assumptions for design for the limit state of collapse in flexure. And we will use these assumptions in our next chapter when we look at the limit state of collapse in flexure and we look at the analysis and design of our beam sections for flexure or for bending moment. Similarly, we have the assumption for the design for the limit state of collapse in compression. In addition to the 6 assumptions that we discussed before for the limit state of collapse in flexure, these 2 additional assumptions are also used for limit state of collapse in compression. This we will discuss when we are discussing the design of compression members. That means we are discussing the design of columns. And finally, we have limit state of serviceability. One is the criteria for deflection, which is given in clause 42 of IS 456. And then we have another limit state of serviceability for cracking, which is given in clause 43. These sections also we will discuss in detail when we are discussing the limit state of serviceability in a separate chapter. So this brings us to the end of our chapter 2. In this chapter 2, we discussed on these main topics: safety and serviceability requirements, design strength, idealized stress strain curve, limit state of collapse, and limit state of serviceability. In our next video lecture, we will start with chapter 3 and we will discuss primarily on limit state of collapse in flexure for our beam sections. So I'll see you then. Till then, stay safe and thank you.